because people continue to join, right? Today, we're actually extremely happy to have Professor Takasada Shibauchi, my good friend from University of Tokyo, to give a talk. And he and I actually know for many years. He mostly worked on transport properties on different exotic materials as well as superconductors. And when I look at his CV, just today, I realized that he actually is an Oppenheimer Fellow at Los Alamos. That's actually extremely a distinguished fellowship, very hard to come by. So he's stayed in the U.S. for some time, and he's been at the University of Tokyo for the past 10 years as a full professor. Yeah, so he's really prolific and doing many exciting things. Today, I want him to focus on this the origin of electronic nematic phase in iron selenide. I invited the MIT group to give a talk on that, suggesting it was purely electronic nematicity. And today I see some very interesting papers by Taka on the whole phase diagram of a different doped iron selenide. So I want him to give a presentation on this, so the broad audience can be appreciative of this field. Yeah, thank you, Taka. It's all yours.
Okay, thank you very much, and thank you very much for the kind introduction, Vincent. Okay, so let me give a talk on the nematicity and exotic pairing states in iron selenium-based superconductors. And this material, iron selenium, is very interesting material because it has purely nematic electronic states without having any long-range magnetic order at ambient pressure. And we have evidence for pure nematic quantum critical points in this sulfur and tellurium substituted iron selenium materials. And so then I would like to talk about enhanced pairing strengths by nematic fluctuations in tellurium material. And then finally, I'd like to discuss superconducting gap structures, which seems to have a very exotic pairing states. Okay, so let me, this is a collaborators. So we have many exciting collaborations with very different groups. And most work on transport has been done in my group in the University of Tokyo. And I acknowledge the help of Professor Okazaki-san, who have done the laser ALPS measurement. And also I'd like to acknowledge the Tomo Uemura, who helped a lot about the muon measurements, and others. I'd like to acknowledge these people listed here. Okay, so let me start with the nematic quantum critical points in these materials. So this is a general phase diagram, temperature versus some kind of non-thermal control parameter. And one can suppress the ordered phase, by tuning this control parameter G. And at some point, you can have the so-called quantum critical point at which you have a second order phase transition at zero temperature. And what is interesting here is that above this quantum critical point, we have a so-called quantum critical regime. And in this regime, we can sometimes have the very exotic properties, including the deviations from the conventional frame liquid theory of metals. And what is more interesting is that one can have the superconducting dome around this QCP. And there is a lot of discussion about the origin of this superconductivity, which may be unconventional, which is related to the quantum critical fluctuations of this ordered phase. Because near the QCP, we have a very enhanced quantum critical fluctuations of this ordered phase. And this kind of idea has been used to explain the, for example, the superconducting dome in heavy-fermion or cuprates, and in which the antiferromagnetic spin fluctuations are important. And I think it is likely that this superconducting dome in heavy fermions, at least, is likely responsible for the unconventional superconductivity. So now the question here, which I would like to address today, is that if we have the non-magnetic ordered phase here, for example, we have this kind of electronematicity, then we have the kind of quantum critical nematic fluctuations around this QCP. Then the question here is that can nematic fluctuations enhanced near the QCP promote ITC superconductivity or not? So this is the question which I would like to address today. So if you look at theory, there are several theoretical proposals on this kind of nematicity-induced superconductivity. For example, this is a paper by Kontani-san's group, in which they kind of consider the orbital order or quadrupole order, and you can actually have nematic or orbital fluctuations near this QCP, and you can have the superconductivity around here. Also, here is a paper by Steve Kilberson, and they also consider the nematic order, and we can have a superconducting dome. And near the QCP, we have a very unusual scattering in the resistivity. So this kind of nematic fluctuation mediated superconductivity has been, tested in the iron-based superconductors, in which we have a very, pronounced electric nematicity below the structural transition from the tetragonal to orthorhombic crystal structure. And this is the phase diagram of the barium 122 based superconductors. And here is the barium iron 2 arsenic 2. And you can either make electron doping or hole doping or even isovalent substitution to suppress this electric nematicity. Then you can actually have the superconducting dome like this. However, in this material, just below this nematic transition, you also have the antiferromagnetic transition TM. And it's almost, coincide with each other. And this is TS and this is TM. And this is the phase diagram for the phosphorus substituted 1 to 2 system. And as you can see, this TS and TN is almost the same, but both of them actually decrease like this, and it disappears at around 30% of substitution. So we have several evidence for the existence of the quantum critical point near this endpoint. For example, we have the very enhanced effective mass from the quantum oscillations or the specific heat, and we can see that the resistivity shows anomalous power of unity around here, which is a signature of the non-Fermi liquid. And then we have this kind of superconducting dome centered around QCP. However, in this case, this QCP is both for this electric nematicity and the antiferromagnetism. So this is actually the antiferromagnetic nematic phase. So it is difficult to pinpoint the impact of nematic QCP on superconductivity because of the presence of the antiferromagnetic QCP. Okay. Now, I think what is more interesting is to look at this iron selenium-based superconductors. And this is a crystal structure, and it has a very simple crystal structure with layered planes of iron and selenium. And what is very interesting here is that we have this kind of structural phase transition, which is driven by the electric nematicity. However, there is no magnetic transition down to 0 temperature at ambient pressure. And this material is, very interesting in many ways because the electron structure is very interesting as well, and it has a compensated semi-metallic electron structure with very small Fermi energies. It only has like 10 millieV Fermi energies. And so this is a very important features for the study of BCS-BC crossover. And also the superconducting gap is very anisotropic like this, okay? And as I mentioned, we have the no magnetic ordering down to 0 temperature at ambient pressure. However, if you apply the pressure, this nematic transition is going down. And before reaching the nematic QCP, we have actually pressure-induced magnetic phase appearing like this. And it has a dome structure like this. And near the end of the high pressure magnetic phase, we have the enhanced superconductivity like this. Okay. So unfortunately, this physical pressure is not a very good tuning parameter to have this purely nematic QCP in this material. So what we have been working on is that we can use the isovalent substitution, which can be identified as a kind of chemical pressure effect. And then also we can suppress this nematic transition. And in this case, we don't have any magnetic order appearing, in this phase diagram. So we can actually have a purely nematic QCP around 70% of substitution, which is very good. And what is important to have this kind of system is that we can obtain high quality single crystals by using the so-called chemical vapor transport technique. And here is a set of images of the STM and the topographic images. And you can easily identify the position of sulfur atoms like this. And in a wider view, as you can see there, the distribution of sulfur atom is quite uniform, and there is no evidence for any segregation. So which means that we have a uniform crystal. And also we can clearly see the beautiful quantum oscillations at high magnetic field in a wide range of the sulfur content. So meaning that our crystals are quite clean all over this X range. And what is more important in this quantum oscillation results is that there is no evidence for band folding at any X, meaning that there is no evidence for antiferromagnetic order. So this endpoint of nematicity is kind of pure nematic QCP without having any magnetic order, and which is evidence from the enhanced nematic susceptibility, which can be measured by the elastoresistance measurements. And this nematic QCP has also been suggested from the transport measurements, and this is resistivity as a function temperature of this QCP.
Which kind? Did you check with it? Did you check?
Okay, and it shows the linear resistivity temperature dependence in the normal state. And if we can apply high magnetic field to suppress the superconductivity, this T-linear resistivity actually extends down to a very low temperature. So this is an indication that we have some kind of anomalous transport near the end of the nematicity, which is another evidence for the nematic quantum criticality in this system. Now, there is another system which can be studied. So we can actually substitute selenium with another isovalent tellurium, which is here. But in this case, there is a sample issue about the phase separation by using the usual flux technique. However, we can actually obtain the very high quality single crystals by using the chemical vapor transport. Although the samples are quite small, we can have the single phase superconducting samples throughout these tellurium concentrations. So we can actually identify the nematic transition by using the resistivity and low temperature diffraction technique. And we can kind of make this kind of phase diagram showing that the nematic transition is going down monotonically, and it goes to almost zero at about 50% substitution. Okay, now how can we identify the nematic fluctuation? So we can use the so-called elastoresistivity measurements, which is a measure of the so-called nematic susceptibility. So what we can do is that we can use a piezo device like this and apply the voltage to have this anisotropic strain into the sample, and then measure the resistance response. And then we can use the two different geometry to have the different symmetry. So this is the B2G symmetry, and this is B1G symmetry. And then we can make the so-called elastoresistivity tensor, which is the actually directly related to the nematic susceptibility. So, for example, if you want to measure the magnetic susceptibility, the order parameter is the magnetization, and the conjugate field is the magnetic field. So DMDH is the susceptibility. And in this case, nematic susceptibility is the the response of the nematic order parameter, which is the basically resistivity anisotropy, and conjugate field is the uniaxial strain. So d eta d epsilon is the nematic susceptibility. So one can measure this kind of elastoresistance following the technique developed by the Ian Fisher's group in Stanford. We can actually have a set of data of the temperature dependence of the 2M66, which is this B2G nematic susceptibility. And as you can see, it shows the Curie-Weiss-like temperature dependence above the nematic transition temperature. And we can fit this data by using this simple Curie-Weiss law, from which we can estimate this Curie-Weiss temperature T0. And T0 is basically the bare nematic transition temperature if we don't have any coupling between the electrons and lattice. And for example, if you look at this data, then T0 is actually lower than actual nematic transition temperature. This is because that there is a coupling between the lattice and electrons, and the thermodynamic nematic transition temperature is actually shifted upwards from the electronic nematic transition temperature, which is T0. Okay, so and by changing this substitution, we can see that this bare nematic transition temperature T0 is changing sign from positive to negative, and T0 equals 0 means that it diverges towards zero, absolute zero temperature, meaning that we have evidence for the quantum criticality. So by using this data, we can construct this kind of phase diagram. So this is a little bit complicated, but this X equals 0 is the iron selenium. And in the left-hand side, we have iron selenium sulfur. And in the right-hand side, we have iron selenium tellurium. And this yellow point is the nematic transition temperature determined by resistivity and X-ray. And these red points are the Curie-Weiss temperature T0, which is the bare nematic transition temperature. Okay, And background, we plot this the magnitude of the nematic susceptibility, which shows an enhancement near the QCP point of the bare nematic transition. Okay, which is which indicates that the quantum critical fluctuations are enhanced near the QCP. And actual, phase transition is shifted up or shifted, to the right or left. And this has been understood by the presence of, as I mentioned, the presence of the coupling between the electric nematicity and lattice. And so this T naught is shifted upwards or rightwards to the thermodynamic nematic transition, TS. And this amount of shift, R naught, is given by this kind of formula. And in the case of iron selenium-based superconductors, this Fermi energy is quite small. So that's why we have a, kind of sizable R naught, the shift from the bare and the thermodynamic nematic transition. So in the presence of the coupling between the electron and lattice, the thermodynamic nematic QCP should be at the end point of this actual nematic transition temperature, so we can identify that we have two nematic QCP in this phase diagram, okay? And below is the actually dependence on TC as a function of composition. And as you can see, we have a very, unusual kind of structures. So inside the nematic phase, we have this kind of one superconducting dome, which we call SC1. And in the selenium side, we have actually suppressed TC, which we call SC2. And then we have another this SC3 is centered around this nematic QCP of this terbium side, okay? So this is a kind of candidate for the nematicity-induced superconductivity. Okay, now we can take a look at the low energy spin fluctuations measured by NMR, because, although we don't have any long-range magnetic order, we may still have the remnant magnetic fluctuations. And so this is 1/T1T, which is a measure of spin fluctuations, and as a function of temperature and doping. And here you can see that, enhancement of 1/T1T near the 10% of sulfur substitution, which seems to correspond to this peak in SC1, okay? So this suggests that this superconducting dome of SC1 may be related to the spin fluctuations, found by this NMR measurements. However, if you go to this SC3 side, what happens is that if you measure 1/T1T, it shows basically flat behavior, meaning that it's a Collin-Haar relation. So there is no evidence for significant spin fluctuation, at least in the very low energy side in this SC3 superconducting dome. Okay, so then, so meaning that we don't have any significant spin fluctuations, but we have evidence for the nematic QCP. So this is likely that SC3 dome may be related to this nematic quantum critical fluctuations. Okay, so this is very promising. So then we wanna show more. How can we estimate the pairing strengths by these nematic fluctuations? So to do this, we use the actually high field measurements. So this is a set of data for field parallel to the c-axis. So we can measure basically the upper critical field, HC2, by using the resistance and so-called tunnel diode oscillator technique, in which we can see the superconducting transition in magnetic field. Then here is the plot of the TC at constant fields as a function of composition. So this 0 Tesla data is basically the same as this, 3 structures. And then if you apply, let's say, 20 Tesla, then this, for example, SC1 dome shrinks, and SC3 dome also shrinks, but we have completely separated 2 dome structure. And SC2 phase is completely suppressed by a small field. Okay, so this clearly indicated that this SC1 dome and SC3 dome may have different origins. Okay, then what happens is that if you apply more than 20 Tesla, this SC1 dome is completely suppressed, but this SC3 dome is still there. So this means that the SC3 dome is very robust against high magnetic field. And what is more interesting is that even if you apply 45 Tesla, you still have a superconducting dome surrounded by, around this nematic QCP. Now, one can also take a look at the temperature dependence of HC2, and it also changes like, this kind of curvature to this flattening behavior at high fields. If you go from low concentration to high concentration regime. And in the tetragonal phase, outside the nematic phase, we can have the so-called Pauli limited behavior of HC2 at low temperatures, because the HC2 scale is becoming very high. So from this temperature dependence, we can analyze the orbital limit and actual HC2. By comparing these two, we can estimate the so-called Pauli limit of the superconductivity in this system. And this view graph shows that how this H Pauli is changing as a function of tellurium composition. And as you can see, if we make a ratio between the H Pauli and TC, which is a measure of basically the superconducting gap divided by TC, which shows an enhancement towards this QCP point. Okay. By the way, this ratio is expected to be 1.84 is a simple BCS superconductors, so it's already enhanced, by up to a very high value, and near the QCP we have a very high number. And this indicates that we have actually enhanced pairing strengths near this nematic QCP. So from these results, we can conclude that the nematic fluctuations emanating from this QCP can enhance the pairing strengths of field robust superconductivity. So I think this is, first case to show the direct relationship between the superconducting dome and nematic QCP with evidence for the enhanced pairing strengths. Okay. So now you may ask why we have so much difference between the tellurium side and sulfur side. And it is not clear actually at present, but I would like to introduce one theory paper, this paper, showing the possible mechanism of this, okay? And they actually consider, again, this nematolattice coupling And the this R naught is the basically gives the amount of this shift as between this bare nematic transition and actual TS. And if this R naught is smaller than this ratio, meaning that the nematic versus magnetic interaction, then you may have a superconducting dome. So, but in the opposite case, you won't see this enhanced TC. So that's their theory. So in other words, in this tellurium side, we have dominant nematic fluctuations. So we have this situation, and we can see the dome. However, in the sulfur side, we have this kind of situation because we have still strong low energy magnetic interactions. So that's one of the possible explanations why we have so much difference between SC2 and SC3. Okay, now let me go to the most important part of my talk, which is the superconducting gap structures. So this is again this TC dependence, the same picture. So we have two QCPs, and between these two QCPs, we have nematic state, and outside we have tetragonal state, okay? And the another interesting thing I have to mention is that in this SC3 part, we have, electron structure becomes topologically non-trivial. And one of the Kalkgen band is coming down to the Fermi level, making the electron structure becoming topological, okay? And then there is evidence for the, topological surface states like Dirac-like states like this for x equals 0.5 or something like that. And this indicates that we indeed have the, topologically non-trivial electronic states. Then you have a superconductivity below like 15 Kelvin. Then you may have a topological superconducting state. So that's why people are very interested in this iron selenium tellurium in this tetragonal side. Okay. However, very recent results of ARPES below TC shows that this Dirac cone is actually have a kind of Dirac gap like this. And this suggests that maybe in this superconducting state, we have a time reversal symmetry breaking state. Okay, so this is one interesting aspect of this material. So now we want to take a look at the superconducting gap structure. So let's start with this SC1 phase inside the nematic phase. And here is the C over T, the specific heat as a function of temperature. And it shows the basically T linear-like behavior at low temperatures, meaning that the superconducting gap is very anisotropic. And if you measure the STM spectra, you will see that it shows a V-shaped DIDB at low energies. So this is also consistent with the anisotropic superconducting gap. And this is also consistent with the QPI results, showing that superconducting gap is strongly anisotropic. Then if you go to the SC3 side, what happens is that the C over T is showing this kind of very flat temperature dependence at low temperatures, meaning that you actually have a fully gapped state. And this is also consistent with STS, showing this flat behavior or U-shape in the tunneling conductance, okay? So it seems to me that SC1 and SC3 has kind of different superconducting gap structure, which is actually consistent with the different mechanism of the superconductivity between these two phases. And if you go to SC2 side, outside the nematic phase in the ion selenium sulfur, we see a very unusual situation. So this is a C over T as a function of T, showing that we have a very large residual density of states at low energies like this. And we also see a very strong superconducting fluctuations. And the STS spectra also shows a very damped structure. And we have a finite zero bias conductance. Okay, so it seems to me that this SC2 is a very exotic superconducting state. So how can we understand this? So to explain this, we can actually go back to the general classification of the superconducting gap structure. So as you know, we can have a different gap structure like fully gapped state in S-wave superconductors, or point nodes, which is a zero-dimensional node, or line nodes, like meaning that one-dimensional node in, for example, D-wave superconductors, right? And by looking at these different gap structures, you can measure, for example, low energy quasi-particle density of states, which shows a different behavior. And for example, in the line node case, you have linear dependence of the quasi-particle density of states. And then actually, if you apply a magnetic field in the line node case, what happens is that we can have this so-called Doppler shift mechanism to have the Borovic effect, in which you can actually create the low energy density of states quickly. Because if you apply a magnetic field, we can induce the superconducting vortices, and around the vortices, we have a supercurrent, which makes the Doppler shift of the quasi-particle density of states. Okay, so this has been actually well known for the line node superconductors, and this has been used to detect the the presence of line nodes in the superconducting gap. So far, so good. However, very recently, there is a theoretical suggestion that we may have a completely new class of superconductivity showing the two-dimensional nodes, which is called Bogolyubov Fermi surface. So in such a case, there is a finite density of state even at the zero energy. So it's like a metal, even though it's a superconducting state. And to have this kind of very unusual superconducting state, we need to have the time reversal symmetry breaking in the superconducting state. And this kind of very interesting idea has been first developed by Daniel Agterberg, and this is a seminal paper. And basically, they start with the Bogolyubov-Jan Hamiltonian and make anti-symmetry matrix by using this kind of trick. Then one can mathematically define the so-called Pfaffian of this Hamiltonian. And so I'm not a theorist, so I cannot explain the details, but I can say that Pfaffian equals zero gives the zero energy states. So for example, in the normal state, Pfaffian shows this kind of, is given by this kind of formula. So zero energy states, Pfaffian zero gives the Fermi, basically Fermi surface like this, okay? And if you go into the superconducting state, usually this Pfaffian becomes positive or non-positive, right? And or non-zero. And the Paphian zero gives the nodes, actually, which is actually either zero-dimensional or one-dimensional. However, if the time reversal symmetry is broken, they actually have shown that you may have a solution that Paphian becomes negative for some k. And it's not, always becoming negative, but you can find some parameter range in which you can have a negative Paphian. Then you can have the Bogoliubov frame surface or two-dimensional nodes. And in this particular example, you can see this orange torus. And inside the torus, the Paphian is negative. And if you go from inside to outside the torus, the Paphian changes sign. And this surface, on this surface, Paphian is zero, okay? So this Bogoliubov frame surface is topologically protected if Paphian is negative. Okay, so that's the kind of very interesting idea. So one can understand, I'm an experimentalist, so I talked to Daniel and he can explain that you can say that this can be understood by the spontaneous Bogoliubov effect in the absence of magnetic field, meaning that if you have the time reversal symmetry breaking, it's like you actually have an internal magnetic field without having the applied magnetic field. So that can induce the Bogoliubov effect if you have nodes in the original electric structure. Then you can spontaneously have the Bogoliubov effect, which induces the zero energy states. So if you go back to here, so Bogoliubov effect can induce the zero energy state. So that's why you have the zero energy density states even at zero field. Then the group of Peter Hirschfeld have considered this possibility for iron selenium-based superconductors. So they actually assume that the time reversal symmetry is broken. And in their Hamiltonian, this small delta is the parameter which defines the degree of time reversal symmetry breaking. And then they can find some parameter range in which Paphian can become negative. So that's why, they can suggest that in this iron selenium-based material, we may have a Bogoliubov frame surface, and they call this state as ultranodal pair states. So here is a kind of some electron structure they calculated, and in some parameter range, they see this blue region in which you have a Bogoliubov frame surface. And if you have this, you can easily understand why we have a finite residual C over T or finite zero bias conductance effects. So these kind of results are consistent with the our experimental data C over T and tunneling spectra in the tetragonal SC2 phase of iron selenium sulfur. Okay. Again, so this is the comparison. So this is again the iron selenium sulfur phase diagram determined by the specific heat. So this is the nematic transition. And what happens is that TC is actually jumped from like 10 Kelvin to 4 Kelvin. And at the same time, specific heat shows a very dramatic change. And only in SC2, we have this large residual density of states. So there seems to be some kind of, completely different superconducting gap structure between SC1 and SC2, and TC also, quite different. Now, the question is that do we have evidence for time reversal symmetry breaking? Because to have this kind of ultranodal pair state with Bogoliubov film surface, the most important ingredient is that we need to have time reversal symmetry breaking in the superconducting state. So to test this, we actually conducted zero field μSR measurements with the help of Tomo Uemura. And basically, what we see is the time dependence of μSR asymmetry, which is a very sensitive probe of the internal magnetic field. And we can analyze the data to extract the μSR relaxation rate as a function of temperature at zero magnetic field. And as you can see, we have an enhancement of relaxation rate below TC. In all the cases, for example, in iron selenium, we see this, and this is the sulfur side, Sc2, and this is Sc3. We also see this. So to our surprise, we see the evidence for time reversal symmetry breaking for all Sc1, Sc2, and Sc3 phases, okay? But at least for Sc2, we have this evidence for time reversal symmetry breaking. So one of the most important requirements is fulfilled for this, the presence of Bogoliubov film surface. Now, one can also take a look at the amount of the internal magnetic field as a function of concentration. And what we found is that Sc2 and Sc1 is kind of similar in terms of internal magnetic field, but Sc3 shows a much larger internal magnetic field. And this time reversal symmetry breaking in the Sc3 phase seems to be consistent with the recent ALPS measurements showing the Dirac gap in the surface electron structure. So it seems to me that this topological time reversal symmetry breaking state seems to be different from the Sc1 and Sc2. So here is a set of data summarizing our kind of results for iron selenium sulfur. So again, this Sc1, we have a nematic phase, and TC is higher than Sc2. And if you look at the zero bias conductance, which is plotted by this brown dots, and also the residual density of states from specific heat, which is plotted by this pink one, you can see the sudden increase in the Sc2 phase in the tetragonal side. And also we can take a look at the transverse field μSR measurements, from which you can determine the superfluid density, 1 over penetration depth squared, which is related to the superconducting carrier density divided by the effective mass. And this superfluid density is plotted by these red points. And this can be compared with the normal state film surface structure, and one can estimate the total carrier number divided by m star, which is shown by this blue dashed line. And as you can see, in the tetragonal side, we have a strong deviation between the superfluid density and normal state n over m. So this indicates that in the tetragonal Sc2 side, we have, substantial portion of the electrons remains ungapped or remains normal. So this seems to be kind of, suggesting to have some kind of film surface is left in the superconducting state. And very recent calculations by Peter Hirschfeld group shows that diamagnetic current response, which is K here, this is related to superfluid density, is changing as a function of delta, which is the degree of time reversal symmetry breaking in their Hamiltonian. And they found that in this hatched range, Bogoliubov Fermi surface becomes stable. And in this region, this superfluid density is expected to, reduce from the original value. So this seems to be quite consistent with our NMR measurements. So from combining these results, we believe that we have evidence for ultranodal pair state with Bogoliubov Fermi surface in iron selenium sulfur only in the tetragonal region. So one may ask then why we have time reversal symmetry breaking in all the time, right? And then, so this is again the phase diagram of iron selenium sulfur. And basically what we have seen is that time reversal symmetry breaking has been seen both in these two superconducting phases, right? However, the evidence for Bogoliubov Fermi surface is only found in SC2 region from the sizable low energy excitation and suppressed superfluid density. Okay, then actually from the theoretical point of view, time reversal symmetry breaking is one of the requirements, and you still have to tune the parameter range to have the Bogoliubov Fermi surface. And what is very different in SC1 is that we have a nematic phase. So we have this so-called nematic twin boundary, right? And the effect of this kind of nematic twin boundary has been first developed by Manfred Sigrist for YBCO, because YBCO has an orthorhombicity and it has an orthorhombic twin boundary, okay? So then, because of the orthorhombicity, D wave and S wave becomes, belongs to the same irreducible representations, and one can mix these two states. And near the twin boundary, which is x equals 0 here, you can actually change the sign of the, relative strengths D and S. So if you go from D plus S, you can go to D minus S in the other side. Okay, then near the twin boundary, you flip the sign, and near the twin boundary, the Manfred shows that you may have the time reversal symmetry breaking. Then, if you go to lower temperature, you can actually still break the time reversal symmetry inside the work. So there is a kind of discussion about the time reversal symmetry breaking in the, this orthorhombic superconductors. So that's one of the possibility to have this time reversal symmetry breaking in SC1, which is different from SC2. However, there is still an open question. Why does the suppression of nematicity drive the topological transition from, this kind of time reversal symmetry breaking state to a ultranodal superconducting state with Bogoliubov Fermi surface? Okay, so now let me just show you very recent results by Okazaki group, who have done the laser RPS measurements in the SC2 phase in the tetragonal side of iron selenium sulfur. And basically, so they use the laser RPS so they can have a very high energy resolution, and they can go down to 2 Kelvin, which is very low below TC. And if you look at the normal state electronic structure, it shows a C4 symmetry, which is consistent with the tetragonal crystal structure. However, if you go to the superconducting state, and if you go look at the phi equals 0, which is this direction, basically they don't see any opening of the superconducting gap. However, if you go to phi equals 90 degrees, which is here, they start to see the superconducting gap, okay? And they can analyze the data to extract the gap size as a function of Fermi surface angle phi, which is like here. They see a gap at 90 and 270 degrees like this. And we have a kind of extended angle range in which we don't see any superconducting gap. So this seems to be consistent with the presence of extended Fermi surface or two-dimensional nodes in the superconducting state of this material, okay? And what we were surprised is that the this gap structure shows twofold anisotropy, although it has a tetragonal crystal structure and it has C4 symmetric electron structure above TC. So this indicates that we have somehow the rotational symmetry breaking in the superconducting state. And so we can call this nematic Bogoliubov Fermi surface or two-dimensional nodes with twofold symmetry. And it's not quite clear why we can have this kind of rotational symmetry breaking. However, we have already two theoretical proposals for this nematic Bogoliubov Fermi surfaces. One is from Peter Hirschfeld group, and one is from the Daniel Agterberg's group. And I hope, we can actually understand more about this by further studies. And finally, here is 1/T1T NMR measurements in the 3 compositions for iron, cerium, sulfur. And actually what we found is that outside the nematic phase, which is the 18%, which is shown by this purple, 1/T1T shows in the superconducting state shows usually, decreased trend. And if you have, strong anisotropy of superconducting gap, you don't have a so-called coherence peak, and it shows a sudden decrease. And it may have a power law temperature dependence below TC. And at the end, you can actually have a finite 1/T1T if you have some kind of impurity effect. However, in the case of 18%, we have actually kind of very unusual upturn at low temperatures, which I don't think it's very, it's not observed in any superconductors so far. So I think this indicates that we still have some spin fluctuations, which may be coming from the nesting behavior between the Bogoliubov Fermi surface. Okay, so I think time is up. So let me put my summary here. So we have kind of studied the iron selenium-based superconductors. So we have 3 different superconducting states, SC1 inside the nematic phase, and SC2 outside in sulfur, and SC3, we have a dome in tellurium. And the SC1 seems to be related to spin fluctuations, and it has an anisotropic gap. And SC3 has a fully gap state, and possibly it's coming from nematic fluctuations because it's surrounded around the QCP of nematicity. And time reversal symmetry breaking has been observed all the way. And only SC2 shows a very unusual Bogoliubov Fermi surface, which is a very exotic superconducting. And I think there are many open questions yet, and but I think this material is very interesting.
Yeah, I agree.
And yeah, we should still work on this. Thank you very much for your attention.
Yeah, thank you, Taka. Yeah, so let me take the privilege and try to ask you several questions. So one question I have is that you said that in the 20% regime that you have a breaking of the superconducting gap in the tetractile state, and you also have a time reversal symmetry breaking. So presumably the time reversal symmetry breaking is for some sort of a ferromagnetic moment along the c-axis, right? So what actually breaks the in-plane, the gap symmetry, as azimuthal angle dependence of that?
Okay, so right, so time reversal symmetry breaking has been implied from the mu-SR measurements.
Right.
So this is basically, detecting the internal magnetic field.
Right.
And if your superconducting state breaks time reversal symmetry, you may have these so-called chiral domains, or if you have some impurity site, at which you can actually have the magnetic field appearing. So, it's
but
not.
I thought the moment is expected to be along c-axis, right? It's not in-plane moment, right?
Okay, so this can be tested by using two different configurations, but our results shows that it's not clear which directions.
I see.
Magnetic field pointing. So, however, as I mentioned, this magnetic field creation is due to, for example, impurities or domain boundary. So it's not clear which direction they choose.
Okay. So then the other question I had, I tried to for Tomo, he did not answer, is that what's the expected moment size for the 15K?
So very small. It's its internal field is about 0.1 Gauss.
Wow. Okay.
So it's not a long range magnetic order.
Okay.
So if you have a magnetic order, you can clearly see the oscillations.
Right. That's not seen. Okay.
Yeah, it's not seen.
Okay.
Yeah.
Thank you. So Andreas?
Hey.
Yeah, good to see you. Yeah.
As you have shown that there is a time reversal symmetry breaking over the whole phase diagram.
Right.
But the explanations are different on the right and the left-hand side. Yeah. So my question is, can you say something about how homogeneous time reversal symmetry breaking is? Because the proposal with the twin boundaries should be very inhomogeneous. Do you see any evidence for that?
Okay, unfortunately, this mu-SR measurements is the kind of bulk probe, and there is no sensitivity of the spatial distribution. And so at the moment, we cannot say anything about the spatial homogeneity. However, if you go, sorry, I don't have it now, but if you go to this PRX paper, which reports the position dependence of STM-DRDB.
Yes.
And it shows that actually near the twin boundary, the nematic twin boundary, we have actually the gap is enhanced.
Yeah, as I remember, it's kind of fully gapped, whereas in other places V-shaped. That's why this proposal was put forward. Yeah. But it's not a measurement of magnetization or time reversal symmetry breaking.
So that's the only thing I can tell right now.
Okay, thank you.
Amalia?
Hi, Taka. Very interesting. I have a few questions, but probably I only manage a few. So my first question is about the nematic critical fluctuations. So you mentioned that indeed there is a finite coupling with the lattice, so that will have a significant effect also on critical fluctuations, how they manifest. So the theoretical paper you're referring to tells us that they only exist along certain directions, the critical fluctuations. So my question is, how do you expect critical fluctuations, which are very direction sensitive, will manifest in experiments which are average out?
That's a difficult question to answer because we don't have particular experimental probe for this. If you have any ideas, we can try to do that. But
well, it makes it difficult to assess this critical fluctuations because of these effects, I think. So there's a mixture of critical and non-critical phenomena.
Right. And I can tell that nematic fluctuations are kind of quite different from the spin fluctuations, because this kind of antiferromagnetic spin fluctuations are non-zero Q, finite Q fluctuations. Mm-hmm. However, this nematic fluctuation is Q equals 0 fluctuations, right?
Mm-hmm. Mm-hmm.
So it doesn't have to be Q. It doesn't have to be Q equal to 0, right? I mean, you can have nematic fluctuations that coupled with spin fluctuation, right?
Yeah, you can have different Q fluctuations, but people talk about this nematicity as a ferro-orbital Q equals 0 nematicity. So nematic fluctuations are Q equals 0, right? So it has a very different physical picture. So this is actually a very interesting point. And from the, I can tell that from this high field experiment, one thing we found is that we don't have we have this enhanced pairing strength, but we don't have any, mass enhancement, actually. Mm-hmm. The H orbital is related to the mass, but we don't see the mass enhancement near the QCP, so which may be related to the different aspect from the spin fluctuation, because in the spin fluctuation QCP, you always see the mass enhancement, right? But here,
particular band, yes. And about the multi-band effects in these materials and the effect of interstitial ions, obviously, which will affect the tellurium, the high tellurium concentration. So what's your opinion when we are dealing with multi-band systems, if they can explain some of the features in upper critical fields, or even the fact that particular Fermi surface might not be involved in pairing?
Yeah, okay, so actually there is a lot of discussion that if you approach iron tellurium side, which has an antiferromagnetic phase, you have the possible orbital sensitive mode transition, orbital selective mode transition, and mass is enhanced towards this direction, right? But this is actually close to this antiferromagnetic phase. And indeed, actually, we originally thought that this kind of superconducting dome is symmetric around the QCP, but it has a kind of, flat behavior toward this high concentration regime, which may be related to the, strong correlation towards this iron tellurium side. But, from HC2 measurements, we cannot have any, information on which orbitals are important and which are not. This is not.
So are you actually suggesting, Taka, that at the 0.5, it's the Q equal to 0 nematic fluctuations, which corresponding to ferromagnetism, that's giving rise to higher TC? Is that what you're suggesting?
Yeah, that's.
I see. That's actually could be extremely, exciting, right? It's because so that basically,
this is true. It's a kind of new mechanism of superconductivity.
Okay.
Beyond the spin fluctuation.
Okay. I hope you're right. We shall see. Yeah.
Yeah.
Thank you.
So, yeah. Okay.
Any other questions? Okay. If not, yeah. Thank you so much, Taka. It's a great talk.
Yeah, thank you very much.
You getting up so early. Yeah. Yeah. Thank you.
I can see some chats.
Yeah. It's recorded.
Yeah, so this is already, yeah, okay.
Yeah, thank you. Yeah, bye-bye.
Okay.